So after this class is over with, I will post the recording in the announcements and in the weekly overview. Okay, so all right. So again, I will post the recording for today here in the weekly announcements. The daily announcements, just like I've been doing. And also, if you've gone to the weekly overview, you see that for each day class meeting, I've been posting the video. So you'll have access to this once I get a link to the video from the stream system. It generates a link and then emails me, and then I'll post a video for you so you have access to it if you want to go back and review it. So we're continuing our study of thermodynamics. My goal today was to solve some problems with you that deal with, that deal with heat transfer, and then we'll talk about thermodynamics, and then I can answer any questions you might have. So bear with me for a second while I get to some material that I want to use. And I'll post a link to these items for you. Oh, wait, no, wrong folder. Let's see. I'll get there in a minute. Just trying to remember where I hit it at. There we go. All right. So I will share a link to this material after I'm done. I'll put it in the required readings viewing section. All right, so I'm going to go into this packet. And just to remind you, on Tuesday, we looked at temperature. We looked at the idea of thermal energy. And then I introduced the idea of heat transfer. But what I did not do was to solve some problems that dealt with heat transfer. And so what I want to do is look at heat transfer when we have a temperature difference, and that requires that we utilize the specific heat constant. And you can see an example of a table that has the specific heat values for different materials. And so we utilize this formula when we want to look at the amount of heat transferred in or out when a material is undergoing a temperature difference. And since that each material will behave differently in terms of the amount of heat transferred, because of each material having its own specific heat value, we want to look at some sample problems that utilize this heat transfer formula. So just as a refresher, in this formula, Q stands for heat, and it is measured in joules. M stands for mass, measured in kilograms. Delta T, that is our change in temperature, and we can find that by taking our final temperature minus our initial temperature. And remember the very important concept, the temperature difference, delta T, change in temperature, is the same on the Kelvin or Celsius scales. And we'll see that play out in the examples that I'm going to work. The other important idea when we're dealing with heat transfer is that if we're putting heat into a system so that heat is being gained, Q is positive. If we are removing heat from a system, then Q is negative. And so we need to follow that guidance whenever we're dealing with heat transfer. Heat in, Q is positive. Heat out, Q is negative. All right, so let's look at some sample problems that deal with heat transfer where there is a temperature change. So it says a 32-gram silver spoon cools from 60 degrees Celsius to 20 degrees Celsius. How much heat is lost by the spoon? So they gave us the mass, the start and final temperatures. And then if you look on the chart that they provided, CP for silver, CP for silver is given as 235 joules per kilogram Kelvin. So we need that value to solve this problem. All right. So we have it here for CP. Remember, CP is a constant for each material. It has its own value. So we can utilize the formula Q equals M delta T times CP. And in this case, they gave us the mass as 32 grams. But we have to remember to utilize this formula, the mass has to be in kilograms. So we convert 32 grams to 0.032 kilograms by dividing by 1,000. But that's just a simple unit conversion that by now all of you should be capable of doing. The temperature difference, delta T. To get the temperature difference, remember we take the final temperature minus the starting temperature. And that gives us negative 40 degrees Celsius. So this material, this silver spoon, is losing heat. And as a result, the temperature is dropping. And that is why delta T comes out negative. So negative 40 degrees Celsius temperature difference. Well, a negative 40 degrees Celsius temperature difference is the same as a negative 40 Kelvin temperature difference. And that's important because when we go to solve our problem, if you notice here, the temperature difference is given as degrees Celsius, but the specific heat value is given using Kelvin. Well, the only way you're going to be able to properly cancel out units is if this is rewritten as negative 40 Kelvin. So even though they didn't show that step in this example, there is a substitution here to allow for the fact that negative 40 degrees Celsius temperature difference, delta T, is the same as negative 40 Kelvin, delta T. So with that being said, we can cancel out our kilograms, can cancel out our degrees Celsius, which is equivalent to Kelvin. So we can cancel that out. And the only thing we're left with is joules. So when we multiply out, we get negative 301 joules of heat. What does that mean? If it's negative, it means we're removing heat. And that has to happen if we want to cool this spoon. All right. Another example. How much heat is required to warm 230 grams of water from 12 degrees Celsius to 90 degrees Celsius? So in this situation, in this example, we are actually raising the temperature of the water. So that means we got to put heat in. So we know in the end, if we're putting heat in, Q has to be positive. Well, they gave us the mass, 230 grams. And of course, we need to convert that to kilograms. They gave us a start and final temperature. So we can easily find delta T by taking what the final temperature minus the starting temperature. So we get a temperature difference here of 78 degrees Celsius or 78 Kelvin, because again, delta T is the same on the Celsius and Kelvin scales. And so we look up CP for water. It was given on the chart, 4,184 joules per kilogram Kelvin. Now just substitute into the formula. M is 0.23 kilograms. Delta T is 78 degrees Celsius. CP is 4184 joules per kilogram Kelvin. So when we multiply that out, we get 75,061 joules. So remember, we have to multiply the numbers, but we have to cancel the units properly. The kilograms cancel, and we're canceling degrees Celsius here and Kelvin because technically they're equivalent. 78 degrees Celsius temperature difference is equivalent to 78 Kelvin temperature difference. So the Kelvin cancels out with the Celsius in this case because they're actually equal. So this is an extremely large amount of heat that is required to raise the temperature of the water. And that is because water has a much larger specific heat capacity. What does that tell me? That if I want to heat up water, it's going to take a lot of energy. That is, it's going to take a lot of heat. Well, remember, heat is a form of energy, right? So if you are, looking at your appliances in the household, you'll find that the hot water heater is the most intensive energy, heat intensive appliance that you have because it's dealing with a material, water, or substance, water, that has one of the higher specific heat values. It also means that once the water is hot or warm, it will hold or retain heat better than other materials. So if we look at the example above, for example, with the silver, it doesn't take nearly as much heat in terms of the heat we have to remove to cool down silver. Why? Because it has a much smaller value of specific heat. And if a material or a substance has a small specific heat value, it means you can heat it up and cool it down very easily. Well, that's not the case with water. It takes a lot of energy. It's much more difficult to heat up water, and then once it's heated, because it has a large specific heat capacity, it can hold its heat much better. All right, so those are two examples in this packet that you'll have access to on Canvas that show how to do heat transfer problem. I have one additional problem that I've solved for you that we can take a look at. Oh, and by the way, this example that I'm about to work comes from this packet, which you also have access to. I just pulled this example out to, single it out as having been solved. All right. So it says, how much heat must be added to 1 kilogram of copper to raise its temperature from 20 degrees Celsius to 100 degrees Celsius? So we want to heat this copper up. We want to raise the temperature. And so anytime we want to put in heat as a means of raising the temperature, we have to go to our specific heat formula. Heat transfer. Sorry about that. Having puppy issues this morning. So in this particular problem, we're raising the temperature. And so we're going to have to put heat in. And so we go to our specific heat formula. They gave us the mass in kilograms in this problem, so we don't have to do any converting. We know the temperature difference is found by taking the final temperature minus the initial temperature. That will give us 80 degrees Celsius temperature difference. And then we just look up the CP value for copper. Now, in this particular example, we're using a chart where the specific heat values are written as decimal values. In the packet that you have, if you look through it, there's a chart. And because they're writing the CP values as a decimal, they're multiplying here by kilo, the prefix kilo, 10 to the 3. It doesn't much matter to me whether you write it as joules or kilojoules, as long as you set it up and solve it correctly. Whatever chart you have, take the value for CP from that chart, and utilize it. As long as you solve the problem correctly, no issues. Okay, so we substitute the mass, 1 kilogram, substitute the temperature difference, 80 degrees Celsius, and substitute our value for CP, 0.386 kilojoules per kilogram Kelvin. Well, in this particular example, I went ahead and took the extra step because I wanted you to see how we properly cancel the units, and that is because we can substitute for 80 degrees Celsius temperature difference, a 80 Kelvin temperature difference. And so when we do the multiplication, we get 30.88 kilojoules, or close to 31,000 kilojoules. I mean, 31,000 joules. Sorry. So we can see here that our Q comes out positive, and that is because we're putting in heat. The nice thing about this formula is when you are putting in heat, it'll turn out positive. When you are removing heat, it will automatically turn out negative if you do your subtraction with the temperature difference correctly. All right. So those are some examples of the heat transfer formula when you have a temperature difference. All right. So the next example that I want to solve gets into heat transfer with a phase change. So I talked about that on Tuesday, and my the information that I shared talked about the idea that when a material is undergoing a change of state, the temperature is going to remain constant. So we can change the substance from one state to another. Remember, our states are solid, liquid, gas, or our phases are solid, liquid, gas. And so when a substance is undergoing a phase transition, for example, if you are boiling water, while that material is changing from a liquid phase to a gaseous phase, its temperature is going to remain constant. And so if the temperature is remaining constant, then that means delta T is 0. If we put in delta T equals 0 into our specific heat transfer formula, then we're going to get Q equals 0, which is absolutely ridiculous because there's no way we can change water from liquid to steam without heating it up. So we have to have a different formula to look at the heat transfer in this situation, and it's called the latent heat formula. And you see the formula written there, Q equals mL, okay? That is the latent heat transfer formula, where M is mass and L is this latent heat constant. Now, we have to be very careful with this formula though, because each material will have its own value of LF and LV. LF is what we call the latent heat of fusion constant. And so each material has its own latent heat of fusion constant. So when we are doing transitions between liquid and solid, we use LF. In other words, when we are doing any kind of transition around the freezing point, we use LF. What kind of transitions are between liquid and solid? So you could be melting the ice in the case of water, or you could be freezing the liquid water to make it a solid. In either situation, you are making a phase transition around the freezing point. And we know for water, that is 0 Celsius. What about this other constant, LV? That is the latent heat of vaporization. And every material has its own latent heat of vaporization. And these are, we use LV whenever we're doing transitions around between liquid and gas. So we're working around the vapor point or the boiling point. Sometimes you'll hear it referred to. So what kind of transitions are those? Well, that's, for example, in the case of water, where we're changing the liquid to steam or vaporizing it, or condensing the steam back into a liquid. Okay, so evaporating and condensation transitions, we use LV. So you have to be very careful when you solve problems that deal with latent heat. You have to read the question carefully and determine, should L in this formula be LF or should L in this formula be LV? So what I've done for you is I'm going to work example number 12. So example number 12 says, how much heat must be removed from 1 kilogram of steam at 150 degrees Celsius to convert it into 1 kilogram of ice at 0 degrees Celsius? And they were kind enough to give us all the different constants that we need. So you see some of those constants are our CP values. You have CP for steam, and you have CP for liquid water. You also have the latent heat of fusion and the latent heat of vaporization. Remember, the latent heat of fusion is the constant that we use when we are working around the freezing point, and the latent heat of vaporization is the constant that we use when we're working around the boiling point or the vapor point. So in this packet, I have solved this problem for you here. So let me open up and notice I have in this packet, I have the picture version or the PDF version. Some students were saying that when they open the PDF version, it was coming up kind of fuzzy. I see it just fine, but no matter. I put both the original picture and the PDF, so you have duplication of the material. Okay, so let's take a look at this example here. And if at any point you have questions, just unmute your mic and ask me, okay? Because this example is a little bit involved. We have to do it in stages. And it's very important that you understand what I'm doing, but even more important that you understand why I'm doing it, okay? So if we want to take our 150 degrees Celsius steam and eventually convert it to ice at 0 degrees Celsius, we have to undergo quite a few different transitions. Well, first of all, we're changing the temperature from all the way from 150 degrees Celsius down to 0 degrees Celsius. But we are also changing the phase from steam all the way down to ice. Well, we can't do all of that in one step. The way this works is that we can either change the temperature of our material or change the phase of our material, but we cannot do both at the same time. So we have to decide, which formula do I need to accomplish this step by step. All right, so the first thing we're going to do in step 1 is we're going to take our steam at 150 degrees Celsius and we're going to transition it into steam at 100 degrees Celsius. So if you notice in this particular step, we're not changing the phase, but we are changing the temperature. So if we're changing the temperature, we have to go to our specific heat transfer formula, Q equals mCp delta T. Well, they gave us the mass at 1 kilogram. They gave us Cp at 2 kilojoules per kilogram Kelvin. And we know we're dropping the temperature by 50 Kelvin. So that's why it's negative 50 Kelvin. I didn't even bother with substituting in negative 50 degrees Celsius because I know that's the same as negative 50 Kelvin. And if you solve a problem for me, I would expect that you would use delta T in the appropriate unit. So when we multiply 1 times 2 times negative 50, we get negative 100 kilojoules. Okay, because the kilograms cancel and the Kelvin cancels. So if I remove, that's because Q is negative, if I remove 100 kilojoules of heat from this steam, it is going to cool down from 150 degrees Celsius to 100 degrees Celsius. And the question is, well, why did I stop at 100 degrees Celsius? Why didn't I just go down to 0? Because that's eventually what I want to do, right? Well, you have to remember that 100 degrees Celsius is a phase transition point. When this steam cools down to 100 degrees Celsius, it's going to stop. That temperature is not going to change anymore until all of that steam is converted to a liquid, because that's a phase transition point. You can't go past that You can't reduce the temperature anymore until all of that steam is converted to liquid. And so that's what we have to do in step 2. We have to look at how much heat is going to be removed in order to take our steam that's now at 100 degrees Celsius and transform it into a liquid at 100 degrees Celsius. And so we have to notice in this step, we're not changing the temperature, because as long as you're doing a phase transition, the temperature won't change. But the material is going to undergo a phase change, in this case from steam to liquid. So if we're undergoing a phase change and not a temperature change, we need to use our heat transfer, a latent heat transfer formula. And that is Q equals mL. But I have to remember that since I'm doing a transition around the vapor point or the boiling point, I need to use LV. And they gave it to me as 2,260 kilojoules per kilogram. Well, let me substitute. The mass is still 1 kilogram. They gave me LV. I multiply 1 times 2,260. I cancel out my kilograms. I keep my kilojoules. But wait a minute. This formula doesn't have a negative sign in it. Where's the negative sign come in? You have to put it in. See, this is something that you have to be careful with, because the specific heat transfer formula, like we use in step 1, will automatically come out negative if you do the temperature difference correctly. This formula is not going to come out negative automatically. You have to know that in order to accomplish step 2, to change the phase from steam to liquid, you have to remove heat. So you have to put in a negative sign. Because if you miss that, then you will be telling me to change steam to liquid, I put in heat. And that's incorrect. So it's on you to correctly put in the minus sign here. Okay, excuse me just for a moment. All right, I'm back. So now we've done our first 2 steps. And so in our first two steps, we've taken out a total of 2,360 kilojoules of heat. So now we're left with liquid that is at 100 degrees Celsius. So let's do the steps that we need to do to ultimately get this material down to ice at 0 degrees Celsius. So in step number 3, we're going to take our liquid that is at 100 degrees Celsius and convert it to liquid at 0 degrees Celsius. So in this particular step, we are not changing the phase, but we are dropping the temperature. So we go back to our specific heat transfer formula. So let's substitute in. The mass is 1 kilogram. They gave us CP for liquid, 4.2 kilojoules per kilogram Kelvin. And we know we're dropping the temperature by 100 Kelvin. So that's why it's negative 100 Kelvin. So I cancel out my kilograms. I cancel out Kelvin. I'm left with kilojoules. And look, this comes out negative automatically because there's a negative sign. So in order to change this liquid from 100 degrees Celsius to 0 degrees Celsius, I have to remove an additional 420 kilojoules of heat. But I'm not done yet, because I am at the right temperature, but I'm not at the right phase. So step 4, I need to remove some more heat. so that I can change this liquid from 0 degrees Celsius to ice at 0 degrees Celsius. So I go back to my latent heat formula. That says Q equals ml. But I have to be careful here because I am using LF. Why? Because I'm doing a transition around the freezing point, 0 degrees Celsius. That's why when I get in this step here, number 3, once I get to 0 degrees Celsius, I have to pause because I won't be able to do anything until all of this material changes from liquid to ice. So let's substitute in our formula. The mass is 1 kilogram. That gave me LF, 334 kilojoules per kilogram. I multiply that out, but I have to supply this negative sign because I know that I am removing heat to change it from a liquid to a solid. So when I'm done with all 4 of these steps, I add up all the heat that was removed and get the total amount of heat that I need to remove to change this 150 degree steam to 0 degrees Celsius ice. All right. So if you have a question about any of these steps 1, 2, 3, or 4, please feel free to unmute your mic and ask before I start looking at thermodynamics, because this example here is the kind of thing that you would expect to have to do on the final exam. And you're going to have to do these kinds of problems in problem set number 11 as well. So what are your questions? All right. I'll take the silence as y'all got this. All right. So the last thing I want to talk about is thermodynamics.
I just wanted to add up everything. So the answer is negative 3 to 3114.
Let's do it. Let's add it up. So I'll take this one here. So let's do it. Negative 100 and negative 2260. That's negative 2360, right?
Right.
So now let's take, so we got here, let me see, 2360, and we got 420 plus 334. So negative 3,114 is going to be negative. I just did the positive version of it because I know there's a negative sign out front, right?
So that would be the final answer right there.
That would be the final answer, right? That's how much heat you would have to remove.
Okay.
Right.
Thank you.
No problem. I'm glad you asked that question. All right. So now let's get into thermodynamics. And I put this packet out for you to be able to take a look at thermodynamics information. You also have access to it here, NASA Thermodynamics. It's the same website. You have access to it in both places. You could click right here, or you could just click on the link in this document and it'll open up. So let's take a look at this idea of thermodynamics. So what it is, first of all, it's the study of the effects of work, heat, and energy on a system. So what we're looking at with thermodynamics is the relationship between work, heat, and energy. And we know by now that work, heat, and energy are interchangeable. And we're looking at how they relate to one another in these large scale systems. Like, we're not looking at the atoms and the molecules, even though we know heat and temperature and all those things do affect the molecules of a substance. But we are looking at that system as a whole. We're not looking at the atoms and molecules, but we're looking at this on a macroscopic level. Okay, large scale. And so what we'll look at in this packet are the 0th law of thermodynamics, the first law, and the second law. And the zero flaw and the second law, we're just going to take a cursory look at them. We're not going to go in any large detail. But the first law is the one where we'll spend a little bit more time, because I would expect that you could, use the first law to actually solve some problems. All right. So I'll click on that information right from here. So let me click on the zeroth law first. Okay. So the zeroth law, and you may be wondering why a zeroth law. Well, they came up with there's the first, second, and third law in the 1900s actually, but I mean, excuse me, the first, second, and third law in the 1800s, early 1800s. But it wasn't until like better than 100 years later that they figured out this new law of thermodynamics. So it's even more basic than the first, second, and third laws, and so they called it the zeroth law. So they figured it out last, but it should have been first, because it's the easiest and the most basic principle. So that's why that's weird numbering, zeroth law. So it says basically when two objects are separately in thermodynamic equilibrium with a third object, they are in equilibrium with each other. And the blue really kind of summarizes the gist of this law. Objects in thermodynamic equilibrium have the same temperature. So if you put a hot object and a cold object together, the heat is going to transfer from the hot object to the cold object, but it is only going to continue to do that until the temperature is the same. Once the temperature is the same in both objects, no more heat is going to be exchanged because they're balanced. And that's what this law alludes to. Once two separate materials that are in contact, reach the same temperature, they're balanced, they're in thermodynamic equilibrium, because we talk about the idea of forces being balanced, right? But in this case, it is the temperature that's going to remain balanced, and so no more heat is going to be exchanged. All right, so that's a very basic law. Again, we don't solve problems with it because it's a conceptual kind of thing, especially at this level. So that's why I said, just to kind of get a general idea of this zeroth law. And then let me go ahead and do the second law, because it is also one that we will not solve problems with, but just a general concept, right? What is thermodynamics, and what are some of these laws from a basic perspective? So the second law of thermodynamics deals with a property called entropy. In other words, every system has this characteristic, or they call it in thermodynamics a state variable called entropy. And this entropy really talks about how chaotic a system is, disorder, chaos. So that entropy is a measurement of how chaotic or how disorderly a system is. And so when we are dealing with this entropy property, we have to understand this concept of a natural process versus a not natural process. Well, what do we mean by natural process? A natural process is one that happens all on its own. You don't have to do anything to cause it to happen. Well, what kind of process could that be from a thermodynamics perspective? Well, that's heat moving, heat transfer. Heat naturally moves from a hot object to a cold object. You don't have to do anything to make that happen. If you put them in touch with each other, the heat's going to go from the hot to the cold. You don't have to force it. It's a naturally occurring process. Much like if you put a ball on the top of a ramp, it'll naturally roll down. You don't have to do anything to make the ball roll down. That's a natural process. And so for these natural processes, we call them we look at these processes from a reversible or irreversible perspective. Okay, so reversible means that you can undo whatever was done, and then irreversible, you can't undo it. Okay, and so when we're looking at this state variable or entropy, we look at the idea that a natural process that starts in one equilibrium state and ends in another always moves in a direction that causes the entropy of the system plus the environment to increase. So these natural processes that are irreversible processes. So heat goes from hot to cold naturally, and that's irreversible. There's no natural process where heat goes from cold to hot. You have to make that happen. Okay. And so during these natural processes, entropy increases. The final entropy of your system is going to be bigger than the entropy you started with. So what is it saying? For these reversible, irreversible, or natural processes, the chaos in the system automatically increases. Okay. Now, what about these reversible processes? So let's say that there's a reversible process. Well, it means you can undo what was done. And you would think, well, if I undo what was done, maybe the entropy will go down, right? Because if it's a irreversible process, the entropy goes up. So maybe for these reversible processes, entropy will go down. But that's absolutely not how it behaves. Even for a process that's reversible, the entropy is not going to decrease. The best you can do is keep it constant so that your final entropy, remember, entropy is looking at what? How chaotic is the system? So even for a process that's reversible, the entropy is going to stay the same. So looking at this from the second law of thermodynamics perspective, it says what? We don't have a process where the entropy can decrease. We're either keeping it constant or we're increasing it. And so again, there's not that I want you to necessarily solve problems with this, but to understand the basics of what this second law of thermodynamics is talking about. Okay, so now let's take a look at our first law of thermodynamics. Excuse me. And so this first law of thermodynamics says that, so we're looking at this from a perspective of the relationship between work, heat, and energy. Okay. And so we need to have an understanding of this idea of internal energy. So internal really means that what's going on the inside of our system. Well, we know that we don't look at our system from a perspective of looking at the molecules that make up the system. We're looking at this from a large scale perspective. So, but we know something is going on the inside that is causing the amount of energy on the inside of our system to change. And we call that energy that's on the inside of our system, we call it internal energy. Okay, so the first law of thermodynamics looks at how the internal energy changes, how much. We don't need to know the actual inner workings, but we do need to know how much is this internal energy changing in our system. Okay, and that's why it says here, any thermodynamic system in an equilibrium state possesses a state variable. In other words, it's the characteristic of the system that's called the internal energy, E. So these thermodynamic systems that we want to study on a large scale, they all possess this characteristic called internal energy. And if we look at going from one equilibrium state, remember equilibrium means balance, right? So if we go from one balanced state to another, we're going to change the internal energy of our system. Well, that makes sense. If you're making some type of change in your system, you're going from one state to another, the inside of your system is going to change. Now, We don't need to know what happened to make it change. We just need to know it changed. And the question is, how much did it change? Well, if we want to look at how much our internal energy changed, we can take our our final value minus our starting value. Same way we've been doing all along, right? Delta. Delta means take the final value minus the starting value. So that's E2 minus E1. Well, there is a relationship between that change in internal energy and the amount of heat that we put in and the amount of work that we get out. So let's say we put a certain amount of heat into our system, Q, and that allows our system to do a certain amount of work, W. The difference between Q and W tells us how the internal energy of our system changed. So that E2 minus E1 equals Q minus W. Again, I don't really have to know what's going on to make the energy change. I can determine how much it changed simply by looking at Q minus W. So you can think of our system in some ways as like a black box. You can't see inside the black box. You don't know what's going on inside the black box. All you know is you put heat into the black box and the black box does some work, W. Well, without even looking on the inside of the box, you know how much the inside of that box changed simply by looking at Q minus W. And that's what they're doing in the picture. The picture shows a piston. And in the picture, you're pushing down or compressing the piston. This idea of a combustion engine, if you will. Well, we don't need to know about the internals of that. All we need to know is we put in some heat, and as a result, the piston moved. That caused the system to do some work. And the difference between Q minus W tells us how did this piston system change its energy. All right, so the first law of thermodynamics says that there is no process where Q is going to equal W. Well, if Q can never equal W, then Q minus W can never be zero, right? Think about the right side of this formula. If Q and W are equal, when you subtract, you'll get zero. But the first law of thermodynamics says Q minus W will never be zero. In other words, you are always going to lose something in the process. You put in Q, you get out W. Well, if they were the same, if all of the Q you put in got converted to W, then you would have a perfect system, meaning you wouldn't lose anything. You would have a 100% efficient system. First law of thermodynamics says that doesn't exist. So Q minus W can never be zero. Okay? First law of thermodynamics. All right. So we've looked at these items here, this and all four of these. So what I did was I kind of summarized things for you here in several of these pictures. So I looked at here the idea of heat transfer with a phase change. So the three phases of matter, and the idea that when a system undergoes a phase change, the temperature difference is zero, so you don't get any temperature change. And so you have to go to this formula Q equals ml, where you have two possibilities, either LF for freezing point transitions or LV for vapor point transitions. Okay? So I kind of summarized that whole heat transfer with a phase change information for you. Similarly, I summarized the heat transfer with the temperature difference. So this formula is useful when you actually do have a delta T. So you go to this formula. And then the idea that Q stands for heat in joules, M is mass in kilograms, how you find your delta T, and it's the same on the Celsius or Kelvin scales. And then Cp is your specific heat constant. When you put in heat, Q is positive, the temperature goes up. When you remove heat, Q is negative, and the temperature goes down. So I kind of summarized that whole heat transfer with a temperature change for you. Okay. And then finally, I looked at thermodynamics. So I summarized the 3 laws. I apologize for my terrible picture taking. The zero flaw means objects are in equilibrium with the same temperature. The first law looks at the relationship between heat, work, and change in energy. And the second law looks at entropy or disorder and chaos. And so then, since I want you to focus more on the first law, I summarized it for you as well. And that is Q equals delta E plus W. And so since delta E can never be 0, Q can never equal W. That's the first law of thermodynamics. Okay. So in this note packet, you have quite a bit of great information. And if you put that in combination with my notes here, you have a really good picture of temperature, heat, and thermodynamics. And that is very important to you, because on problem set number 11, you're going to have to use that information to answer questions and solve problems. And then, of course, on the practice that you have to do for next Saturday. This Saturday, your practice that's due is, well, yeah, this Saturday, the practice that's due is on thermodynamics. So you'll also need that material to help you answer these questions. Okay. So I'm going to unshare my screen. If you have any questions for me, feel free to unmute your mic and ask your question. Again, I'll be posting this recording as soon as I have a link from the system to, share the video.
Would there? You say that there's never going to be a chance for W and Q to equal each other, right?
That's correct, because that
What
would
if
imply that you have 100% efficient engine, and it doesn't exist.
there's no way in a world that could ever exist?
That's right. That's what the first law of thermodynamics tells us. If that were
Okay.
the case, then you could have cars that were gasoline engines that were totally efficient, meaning every bit of gasoline that you put in gets utilized to, facilitate the car moving, the car doing work. And so that's not going to happen. We know that from the efficiency diagram that we looked at um, earlier, that gasoline engines, combustion engines, like the one I showed in
Okay.
the diagram, are about
Right.
30% fuel efficient, right?
Right.
Yeah. For them to
Is
be
there anything
100%
that's
efficient,
100% energy efficient, like a star or anything?
that star ratings, those ratings are typically done for electrical appliances, right? And we know
Uh-huh.
that electrical processes are way more efficient than our combustion processes. But even those electrical processes are not 100% efficient.
I'm still talking about an outer space star, like fusion and
No,
fission,
no,
and
no.
like,
But
is
if
there
you,
anything naturally occurring that comes close to 100% efficient?
uh, no. I mean,
Okay.
there's some things that come close to it, but they aren't 100% efficient. You know why? Because in addition to our first law, our second law tells us, if you do a little bit more investigating in it, for a
Mm-hmm.
process to be 100% efficient, we would have to get down to absolute zero.
Okay.
So,
All right. I'll
without going into like really complicated concepts there, just
right.
just know that there are certain conditions that have to exist naturally for that to happen, and we're not able to get there. Even with our best
Okay.
equipment, we can't create a perfect vacuum, because to get to absolute zero, you need a perfect vacuum. You need the pressure to bottom out, right?
Okay.
And I don't know how much you've done, like in your plant P-Tech classes, or classes where you have to pull a vacuum, they call it. But
Mm-hmm.
those vacuums aren't never going to be perfect.
Right. All right, I was just curious.
Yeah. I mean, it makes sense to ask, right?
Right.
Yeah.
All right. Well, you have a good weekend.
You do the same.
All right.
All right. With that, I'm going to stop the recording.